Welcome to today's class on functional analysis. Today we will discuss consequences of Hahn-Banach extension theorem. Theorem 7.10. Let X be a normed space over K. A part, let 0 not equal to A belongs to X. Then there is some F in X12 such that F of A equal to norm A and norm F equal to 1. Consequently, norm A equal to supremum of set of all mod F of A such that F in X12 and norm F less than or equal to 1. Proof. Given that A element of X and A not equal to 0, let Y equal to set of all Ka such that K element of K. Then Y is a subspace of X. This is because for X and Y element of Y and KL element of K, we have X equal to some K1A and Y equal to K2A for some K1 and K2 element of K, right? Then Lx plus My equal to L into K1A plus M into K2A, that is equal to Lk1 plus Mk2A, which is an element of Y. Therefore, Y is a subspace of X, right? Okay. Now define G from Y to K by G of Y equal to G of Ka, that is equal to K into norm A. Clearly, G from Y to K is linear. Further, mod G of Y equal to mod K into norm A, since G of Ka equal to K into norm A, that is equal to mod K into norm A, that is equal to norm Ka that is equal to norm y, since y equal to k. That is mod g of y equal to norm y. Therefore g is bounded. That is G is a bounded linear map, so G element of Y12. Further, mod G of Y equal to norm Y implies that norm G equal to supremum of mod G of Y such that norm Y less than or equal to 1, that is equal to supremum of norm Y, since mod G of Y is norm Y, such that norm Y less than or equal to 1, that is equal to 1 since A by norm A is an element of Y such that norm of A by norm A equal to 1. That is norm G equal to 1. Now by Hahn-Banach extension theorem, there exists f in X12 such that f restricted to y equal to g and norm f equal to norm g. Thus, for this f, norm f equal to 1, since norm g equal to 1, right? Further, A belongs to y and f restricted to y equal to g implies that f of A equal to f of 1 into A, since 1 into A is A itself, that is equal to g of 1 into A, and that is equal to 1 into norm A, since g of Ka is k into norm A, that is equal to norm A. That is f of A equal to norm A. Okay. Here we have mod f of A is less than or equal to norm f into norm A, since f is bounded, which implies that mod f of A is less than or equal to norm A, since norm f equal to 1, right? Therefore, norm A greater than or equal to supremum of set of all mod f of A such that norm f less than or equal to 1. This is equation 1. On the other hand, we have f of A equal to norm A. Therefore, mod f of A equal to norm A. That is norm A equal to mod f of A, which is less than or equal to supremum of mod f of A, such that f in x12 and norm f less than or equal to 1. That is norm A less than or equal to supremum of mod f of A, such that f in x12 and norm f less than or equal to 1. This is equation 2. So from 1 and 2, from equation 1 and 2, we get norm A equal to supremum of mod f of A, such that f element of x12 and norm f less than or equal to 1. Okay. B part, let Y be a subspace of X and A element of X, but A does not belongs to Y closure. Then there is some f in x12 such that f restricted to y equal to 0, f of A equal to distance between A and Y closure and norm f equal to 1. Consequently, X element of Y closure, if and only if X element of X and f of X equal to 0 whenever f element of x12 and f restricted to y equal to 0. Now we will prove this B part. We have y is a subspace of X. Therefore, Y closure is a closed subspace of X. This is by Theorem 5.28, which implies that X over Y closure is a normed space with quotient norm. Since A does not belongs to Y closure, the coset A plus Y closure is not 0, in X over Y closure. Therefore, by A part of this theorem, there exists some f tilde in x over y closure dual such that f tilde of a plus y closure equal to quotient norm of a plus y closure and norm f tilde equal to 1. This is by part A of this theorem. Now define f from x to k by f of x equal to f tilde of x plus y closure for x in x. Then f is a linear functional where the linearity follows from that of f tilde, right? Now mod f of x is equal to mod f tilde of x plus y closure, since f of x equal to f tilde of x plus y closure. Which is less than or equal to norm f tilde into quotient norm of x plus y closure. This is since f tilde is bounded. That is equal to norm f tilde into infimum of norm x plus y such that y element of y closure. Since quotient norm of x plus y closure is defined as infimum of norm x plus y such that y element of y closure, which is less than or equal to norm f tilde into norm x. This is because 0 element of y closure, right? Thus we have mod f of x less than or equal to norm f tilde into norm x for all x in x, showing that f is bounded. Okay. Now if y element of y closure, then y plus y closure is y closure, which is the 0 element of x over y closure. Okay. Now since f tilde is linear, we obtain f of y equal to f tilde of y plus y closure, but this y plus y closure is a 0 element of x over y closure. So and f tilde is linear. So f tilde of y plus y closure is actually 0, right? Hence, in particular, f of y equal to 0 whenever y element of y, that is f restricted to y equal to 0. Okay. Again, by the definition of f, we have f of a equal to f tilde of a plus y closure. This is actually the quotient norm of a plus y closure. This is infimum of norm a plus y such that y element of y closure, that is equal to infimum of norm of a minus y such that minus y element of y closure. This is nothing but distance between a and y closure. Now we prove norm f equal to norm f tilde equal to 1. We have mod f of x is less than or equal to norm f tilde into norm x for all x in x. We have already proved this. Therefore, supremum over norm x less than or equal to 1 mod f of x is less than or equal to norm f tilde into supremum over norm x less than or equal to 1 norm x, which implies that norm f is less than or equal to norm f tilde. Here supremum over norm x less than or equal to 1 mod f of x is actually norm f. Okay, which is equation 1. Now we want to prove the reverse inequality. So on the other hand, mod f tilde of x plus y closure equal to mod f tilde of x plus y closure, right? That is equal to mod f of x plus y. This is by the definition of f. Which is less than or equal to norm f into norm x plus y for all y in y closure. This is since f is bounded, that is mod f tilde of x plus y closure is less than or equal to norm f into norm x plus y for all y in y closure. Therefore, mod f tilde of x plus y closure is less than or equal to norm f into infimum of norm x plus y such that y element of y closure, right? That is equal to norm f into quotient norm of x plus y closure. Since this is nothing but quotient norm of x plus y closure. Okay. Therefore, norm f tilde equal to supremum of mod f tilde of x plus y closure such that quotient norm of x plus y closure is less than or equal to 1, which is less than or equal to norm f into supremum of quotient norm of x plus y closure such that quotient norm of x plus y closure is less than or equal to 1. That is equal to norm f into 1, right? That is norm f tilde is less than or equal to norm f. This is equation 2. From 1 and 2, we have norm f tilde equal to norm f. We have norm f tilde is 1. Therefore, norm f equal to norm f tilde equal to 1. Consequently, x element of y closure if and only if x element of x and f of x equal to distance of x from y closure, that is equal to 0, since x is an element of y closure, right? This is whenever f element of x12 and f restricted to y equal to 0. This is the proof of B part. Now C part. Let A1, A2, etc. AM be a linearly independent set in X. Then there are F1, F2, etc. Fm in X12 such that Fj of Ai equal to delta Ij, 1 less than or equal to I, comma j less than or equal to m. Proof: let A1, A2, etc. Am be linearly independent set in X. For j equal to 1 to etc. m, let yj equal to span of ai for I equal to 1 to etc. m and I not equal to j. That is, yj is actually the span of a1, a2, etc. aj minus 1, then aj plus 1, etc. am. Okay, then clearly yj is finite dimensional. Therefore, yj is closed in X. This is by 5.4b and yj equal to yj closure since yj is closed. Okay. Clearly, aj does not belongs to yj closure since yj equal to yj closure. Therefore, by part B, that is by part B of this theorem, we can say that there exists some Gj in X12 such that this Gj restricted to Yj equal to 0 and Gj of Aj equal to distance between Aj and Yj closure, but here Yj closure is Yj, so this is actually distance between Aj and Yj and norm Gj equal to 1. Okay, now take Fj equal to this Gj divided by distance between Aj and Yj then Fj is well defined. Since distance of Aj from Yj is greater than 0. Now, Gj element of X12 implies that Fj element of X12 for j equal to 1 to etc. m, right? Further, Fj of Aj equal to Gj of Aj divided by distance of aj from yj, that is equal to 1, right? Since this gj of aj is actually distance of aj from yj. Okay, this is for I equal to j, right? This is for I equal to j, and for I not equal to j, fj of ai is actually gj of ai divided by distance of aj from yj, that is equal to 0, since ai element of yj and gj restricted to yj equal to 0. Okay, that is, here we got for I equal to j, fj of aj equal to 1, and for I not equal to j, fj of ai equal to 0. Therefore, fj of ai equal to delta ij 1 less than or equal to I comma j less than or equal to a. This is the proof of C part.